Hello, I'm Eric Dubois, and this presentation provides an overview of my book, Multidimensional Signal and Color Image Processing Using Lattices, which was published by Wiley in 2019. The presentation was given as a seminar at the University of Ottawa on February 20th, 2020. The purpose of the presentation is to give an overview of the book in the form of a friendly book review. I'll highlight what distinguishes the book from other works in the field and point out a few of the original contributions in the book. The slide highlights the main themes of the book using the title as a guide. Multidimensional here refers to the independent variables such as space, time, wavelength, frequency, and so on. The signal values can be real or complex scalars, as in grayscale images, or they can be elements of a vector space, such as the color vector space for color images. The independent variables, the domain of the signal, can be continuous, as in real-world space and time, or discrete, generally in computer representations. For discrete domain signals, the sampling structure is specified using lattices, where the word lattice is used here in the same sense as in crystal lattice. I also consider both periodic and non-periodic, also referred to as aperiodic signals. The periodicity of periodic signals is specified using a lattice. Thus, lattices specify both sampling structures and signal periodicity. The main theme of the book is to cover color signals, where the signal value belongs to the color vector space of human vision. The book consists of 13 chapters. After the intro, 4 chapters cover multidimensional signals and systems in the 4 main cases that I consider. These are continuous domain and discrete domain aperiodic, and discrete domain and continuous domain periodic. Chapter 6 covers sampling and reconstruction, essentially conversions between the 4 cases just mentioned. Chapters 7 and 8 discuss the representation of color and signals and systems theory for color signals. The approach is original in many aspects and follows from my 2009 book called The Structure and Properties of Color Spaces and the Representation of Color Images, which was published by Morgan and Claypool. Chapter 9 presents wide-sense stationary vector-valued random fields. This is a basic presentation of random fields, and in particular does not cover Markov random fields. However, it does cover vector-valued random fields, specifically for color-valued. Chapters 10 and 11 present multidimensional filter design and conversion between different sampling structures as 2 specific applications of the theory. Chapter 12 is an original contribution on symmetry-invariant multidimensional signal processing, and it generalizes topics such as the multidimensional discrete cosine transform to more general lattices. Finally, chapter 13 is a self-contained chapter presenting the relative material on lattices needed throughout this book and can be consulted at any time. Chapter 2 presents continuous domain signals and systems. Real-world signals such as the light falling on an image sensor or the light emitted by a computer screen are functions of continuous independent variables, namely space and time. These are typically the input and output of the discrete domain analysis and processing systems we're concerned with. Also, they may undergo continuous domain processes such as optical blurring that we need to model for image restoration. For these reasons, it was important to me to give a characterization of the continuous domain situation before going into the discrete domain case. A multidimensional signal F is a function of D independent variables. So D is the dimensionality of the signals. The domain is RD, the space of real D tuples. We're generally concerned here with D being 2 or greater, but one-dimensional signals are also a special case of this theory, corresponding to D equals 1. The range of the signals that we're concerned with are assumed to belong to a vector space. The simplest case is just the space of real or complex numbers. But color images that we're very much concerned with correspond to a 3-dimensional vector space. We assume that the signals themselves belong to a real or complex vector space, S, that we call the signal space. In particular, this means that it is well defined to add signals, scale them, negate them, there exists a zero signal, and so on. Now, a multidimensional system acts on elements of a signal space. We consider deterministic systems that map an element F of the signal space S to another well-defined element G. Systems can be linear or nonlinear. We'll emphasize linear systems, although some nonlinear systems are introduced from time to time. The square law system and the shift system are two examples of the kinds of systems we'll be concerned with. Linear systems follow the standard definition that will recur for all types of signal domains that we consider. A shift invariant system is one for which the system commutes with the shift operator. Our main focus is linear shift invariant systems, systems that are both linear and shift invariant. For an LSI system, the output G is equal to the convolution of the input F with a specific signal H. The convolution is a commutative operation, and if the signal space contains the Dirac delta, then we find that H is the output of the system when acting on the Dirac delta, which we call the impulse response. An example of such a signal space is the space of tempered distributions, although we don't go into the details of this signal space in the book. The concept of convolution will recur for all types of domains that we consider. An important class of signals are the complex exponential sinusoidal signals that are specified by a frequency vector also belonging to RD. A complex exponential with frequency vector u is an eigenfunction of any linear shift invariant system. The corresponding eigenvalue, h of u, is the Fourier transform of the impulse response evaluated at frequency u. This observation, in fact, provides the definition of the Fourier transform for signals defined on RD. Here's an example of a two-dimensional sinusoidal signal. The unit of spatial distance is the picture height, and so this square image is of size 1 picture height by 1 picture height. Notice that the vertical axis is pointing down. In this example, the horizontal frequency u is 1.5 cycles per picture height, and the vertical frequency v is 2.5 signals per picture height. You can clearly see the 2.5 cycles over the picture height along the y-axis. The Fourier transform, as just defined, satisfies all the properties of the usual one-dimensional Fourier transform, as shown in this table. Some are more involved in the one-dimensional case, for example, scaling by a non-singular matrix, which is property 2.6, or properties involve the gradient, like in 2.7 and 2.8. The book explains and demonstrates all these properties and then provides several examples. The chapter then concludes with a discussion of continuous domain systems related to several differentiation operators. Chapter 3 introduces the concept of discrete domain signals and systems. This is the extension of discrete time signals and systems to the multidimensional case. We're concerned with signals defined on regular sampling structures specified by lattices. Some of the basic properties of lattices are introduced as needed, but a comprehensive overview of the relevant material in lattices is presented in Chapter 13. The presentation largely follows the same outline as for the continuous domain case. In discrete domain signal processing, the signal domain is a discrete set of points in RD called the sampling structure, psi. The main tool used to describe and analyze sampling structures is the lattice, used in the same sense as crystal lattice. A lattice is a discrete set of points in RD that contains the origin and where the neighborhood of any point looks exactly the same as the neighborhood of the origin or of any other point. This can be seen in this illustration of a portion of a two-dimensional lattice. There are many different ways to define a lattice. The following definition is easier to work with than the more abstract definitions. A d-dimensional lattice can be defined to be the set of all linear combinations of d linearly independent vectors in Rd with integer coefficients. The basis vectors, expressed as column matrices, are arranged as the columns of a d by d matrix V called the sampling matrix. We say that the sampling matrix V generates the lattice lat of V. We see here the same lattice as on the previous slide, with two basis vectors that generate the lattice and the associated sampling matrix. Note that I always have the y-axis pointing downward, since this is how TV works, scanning from top to bottom. We list here a few key properties of lattices that make them the ideal setting for a theory of multidimensional signal processing. The basis and sampling matrix for a given lattice are not unique. There may be different, equally convenient bases for a given lattice. If we multiply the sampling matrix by any unimodular integer matrix, which has a determinant of plus or minus 1, the new sampling matrix generates the same lattice. For this reason, the theoretical development should not depend on any particular choice of bases. For those familiar with group theory, a lattice has the properties of an additive abelian group. In particular, the sum and difference of any two lattice points also belongs to the lattice. And so the origin belongs to any lattice. If you shift all the points of the lattice by some element of the lattice, you get back the same set of points. This will allow us to shift signals defined on a lattice and talk about shift invariant signal processing. A unit cell of a lattice is a region such that the set of all shifted versions of that region on the points of the lattice fill the whole space without overlap. The area or volume or hypervolume of a unit cell is the area associated with each sample. It is called the determinant of the lattice. The reciprocal of the lattice determinant is the sampling density, the sampling rate in one dimension. This slide shows two possible unit cells. One is a parallelepiped, and the other is the Voronoi unit cell, which consists of all points closer to the origin than to any other lattice point. In the discrete domain case, the basic definitions of signal space, which we denote here by S sub lambda, system H, linear system, shift invariant system, LSI system, these are all formally the same as for the continuous domain multidimensional system, and I won't repeat them here. For the shift system, TD, the shift D must be a point of the lattice. This makes the shift system well defined. Convolution has a similar form to the continuous domain case, but it's now a sum over points of the lattice rather than an integral. We use the same asterisk symbol to denote convolution, and note that convolution is again commutative. In place of the Dirac distribution, we have the unit sample, delta sub lambda of x, which is a very simple function, 1 at the origin and 0 everywhere else. It defines the convolution kernel H, which is equal to the output of the system when delta sub lambda is applied. And this is called the unit sample response. Complex exponentials are again extremely important in discrete domain signal processing. Complex exponentials have the same form as in the continuous domain case, but are only defined on the points of the lattice. Although they are defined for all frequency variables u in Rd, the complex sinusoids are periodic in the frequency vector. The periodicity is given by the reciprocal lattice, called by some the dual lattice, which lives in the frequency domain. If we add any element of the reciprocal lattice to the frequency vector, we get the identical signal on the lattice. The set of frequency vectors corresponding to distinct complex exponentials lie in one unit cell of the reciprocal lattice. Again, complex exponentials are the eigenfunctions of any LSI system. The eigenvalue is given by the discrete domain Fourier transform of the unit sample response. The Fourier transform expression is again derived by determining the response of an LSI system to complex exponentials. The discrete domain Fourier transform, as just defined, satisfies all the properties of the usual one-dimensional discrete time Fourier transform, as shown in this table. Some are more involved in the one-dimensional case, again, scaling by a non-singular matrix, or those involving a gradient. And the book explains all these properties and provides several examples. This slide shows the Fourier transform of a real exponential function defined on a hexagonal lattice. On the left, we see a perspective view, and on the right, there is a contour plot of this Fourier transform. Several periods of the Fourier transform are shown. And in this case, we see the reciprocal lattice is also a hexagonal lattice. The Voronoi unit cell is shown on the right in the red diamond-shaped region. So this is one period of the Fourier transform. So the details of this example and others are in the book. At this point, I would like to highlight some of the differences between the approach in this book and most other works on multidimensional signal processing. First, the development is done entirely on lattices from the beginning, with rectangular sampling structures as a special case. Most presentations present multidimensional signal processing on rectangular sampling structures and present lattices as a specialized extension. However, non-rectangular sampling is widespread and is used in virtually all cameras and displays. So I use this as a fundamental situation. My presentation does not depend on any specific and arbitrary choice of the sampling matrix. In conventional approaches, discrete domain signals are defined on the integer lattice, ZD. These approaches assume that there's an underlying continuous domain signal which is sampled on a lattice. The signal domain is assumed to be ZD, and this is a basis-dependent representation. The representation changes as we change the basis, and the geometric structure of the signals is not evident. The conventional frequency domain representation is also basis-dependent and normalized. The geometric structure is, again, not evident at all. Our approach preserves the geometric structure of the space and frequency domains. Chapters 4 and 5 deal with the multidimensional periodic signals. The illustration on this slide shows an example of a two-dimensional periodic signal. Periodic signals are of interest for several reasons. For example, masks in image sensors and image display devices are periodic, so their analysis is quite important. Chapter 4 covers discrete domain periodic signals, while Chapter 5 covers continuous domain case. The periodicity of a multidimensional periodic signal is specified by a lattice that we call the periodicity lattice. If we add any element of the periodicity lattice to the independent variable of a periodic signal, we get the same signal value back. For a continuous domain d-dimensional periodic signal, the periodicity lattice can be any d-dimensional lattice. In fact, we've already seen that the discrete domain Fourier transform of a signal on a lattice lambda is periodic with periodicity lattice equal to the reciprocal lattice, lambda star. However, for a discrete domain periodic signal, the periodicity lattice must be a sublattice of the sampling lattice. A sublattice is a subset of a lattice that is itself a lattice. Sublattices play a major role in several later chapters as well, so I will say a few words about them here. Any unit cell of the periodicity lattice defines one period of the signal. As I just stated, the periodicity lattice of a discrete domain periodic signal must be a sublattice of the sampling lattice. One period of the periodic signal contains k samples, where k is an integer that is the ratio of the lattice determinants. The set obtained by shifting the periodicity lattice by any element b of the sampling lattice is called a coset of gamma in lambda. Any two cosets are either identical or disjoint. The number of distinct cosets is k, and the lattice lambda is the disjoint union of these k cosets. This expression will be used extensively should be pointed that the B0 to BK minus 1 are each arbitrary elements from each coset, and nothing depends on their particular value. A periodic signal is constant when restricted to any one of the cosets. This figure illustrates a lattice, lambda, whose points are indicated with squares, with a sublattice gamma, whose points are indicated with bullets. There are 6 samples of lambda associated with each sample of gamma. This figure shows the 6 cosets of the sublattice gamma in the lattice lambda for the example we've been looking at. The 6 cosets are numbered 0 to 5. This numbering is arbitrary, and different numberings are used in different circumstances, as is convenient. With these definitions and notation, we can talk about discrete domain periodic signals and systems. The concepts of signal space, linear systems, and LSI systems have essentially the same definitions as in the discrete domain aperiodic case. The output of a discrete domain periodic signal is given by a periodic convolution, which is a sum of k terms. We use the tilde to indicate that a signal is periodic. The periodic output has the same periodicity with k distinct values. The eigenfunctions of a multidimensional periodic discrete domain LSI system are again complex exponential sinusoids. However, for these sinusoids to be gamma periodic, the frequency vector must belong to the reciprocal lattice gamma star. There are exactly k distinct complex exponentials on lambda with periodicity gamma. The eigenvalues of the periodic LSI system are again given by a Fourier transform expression. The Fourier transform for multidimensional discrete domain periodic signals is the multidimensional extension of the one-dimensional discrete Fourier transform, DFT, and is also called the discrete time Fourier series. The sublattice expression is reversed in the reciprocal lattice domain, where lambda star is a sublattice of gamma star. We also define cosets in the reciprocal lattice domain with coset representatives di that we see in the definition of the MD discrete domain periodic Fourier transform. It should be pointed this Fourier transform can be again calculated with an extension of the one-dimensional fast Fourier transform. And it's indicated how to do this in the book. We can also do a complete theory of continuous domain periodic signals, where periodicity is defined by an arbitrary d-dimensional lattice. This is carried out in chapter 5 of the book. With that case, there are 4 situations that have been studied, as shown on this slide. The table shows the 4 categories of signal with the corresponding categories of Fourier transforms in the frequency domain. In the 4th case of continuous domain gamma periodic signals, we see that the Fourier transform is a discrete domain aperiodic, defined on the reciprocal lattice gamma star. As an observation, we note that each of the signal domains is an instance of a locally compact abelian group. Abstract harmonic analysis treats Fourier analysis on this more general abstract domain. However, we do not follow this approach in the book. This table shows the Fourier transform properties for the 4 categories of signals. The table is provided in Appendix D of the book and is available on the book website, suitable for printing on ledger-sized paper or larger. Real-world signals, such as images and videos, are continuous in space and time. However, we require discrete domain signals for digital image and video processing. Thus, we must be able to convert continuous domain signals to discrete domain ones, a process known as sampling. Likewise, we often need to convert discrete domain signals to continuous domain ones for viewing. Chapter 6 presents the theory for sampling and reconstruction of continuous domain signals with the associated sampling theorems. More generally, we can sample continuous domain periodic signals to obtain discrete domain periodic signals, and also sample Fourier transforms. Chapter 6 covers all these cases and also shows how the results can be used in the evaluation of inverse Fourier transforms. The chapter starts with sampling of multidimensional continuous domain signals. This is described by the basic sampling equation. The values of the discrete domain signal are equal to the values of the continuous domain signal at the points of the lattice lambda. This is illustrated with the sampling of two different continuous domain signals with Fourier transforms confined to a circular region of support. The signal on the left has a Fourier transform with a larger region of support. It has higher frequencies and so faster variations than the signal on the right. We know that a discrete domain signal has a periodic Fourier transform. The Fourier transform of the sample signal is obtained by replicating the Fourier transform of the continuous domain signal on the points of the reciprocal lattice and adding, as shown in the next figure for a certain hexagonal sampling lattice. We see that the replicated versions overlap, causing a confusion of information, an effect known as aliasing. On the right, the replicated spectra do not overlap, so there is no aliasing. The continuous domain signal can be reconstructed from the sample version. This leads to the sampling theorem for continuous domain signals. If the spectrum is confined to a unit cell of the reciprocal lattice, alias-free sampling allowing perfect reconstruction is possible. More precisely, the Fourier transform of the sample signal is given by the sum of the continuous domain Fourier transform shifted to all points of the reciprocal lattice lambda star and scaled by 1 over the determinant of the lattice. If the Fourier transform of Fc has support limited within any unit cell of lambda star, these replicas do not overlap, and the continuous domain signal can be reconstructed from the samples. The sum on the right in the equation above is called the lambda star periodization of Fc, and we introduce a convenient notation for this with the circular arrow. The result can then be written compactly in the formula shown here. If the continuous domain Fourier transform of little fc of x is big Fc of u, then the discrete domain Fourier transform of little fc sampled on lambda is equal to the lambda star periodization of big Fc of u divided by the determinant of lambda. This expression is sometimes referred to as the Poisson summation formula. Chapter 6 considers the sampling of both aperiodic and periodic signals. It also considers the periodization of continuous domain and discrete domain aperiodic signals to create periodic ones. This results in the sampling of the Fourier transforms. All the cases can be summarized in this figure, referred to as the Fourier-Poisson cube. This figure captures the relationship among the 4 types of signals studied in the book. Sampling in the signal domain results in periodization in the frequency domain. Periodization in the signal domain results in sampling in the frequency domain. The chapter goes on to use these results to show how to evaluate inverse Fourier transforms. Inverse Fourier transforms were only considered in the case of discrete domain periodic signals. In this case, the signal space is finite dimensional, and the complex exponentials form an orthogonal basis. So the inverse Fourier transform is straightforward. This is not the case for the other 3 signal domains, and some limiting arguments have to be applied. The chapter concludes with the study of signals and transforms with finite support, specifically when periodization does not result in overlap. Chapters 7 and 8 address the representation of color and the processing of color images, respectively. These chapters are limited to still and time-varying images within the class of multidimensional signals. Chapter 7 focuses on the color vector space used to represent color as it's perceived by human viewers. Chapter 8 then addresses signals and systems theory for vector-valued color signals. These 2 chapters are largely based on my book called The Structure and Properties of Color Spaces and the Representation of Color Images that was published by Morgan and Claypool. Chapter 7 is largely devoted to introducing the color vector space C and studying its properties. The perception of color is caused by light with wavelengths in the visible range of roughly 350 to 780 nanometers falling on the retina of the human eye. The colors perceived by a human viewer with normal color vision belong to a three-dimensional vector space. Any three linearly independent elements of this vector space form a basis. We refer to these basis vectors as primaries. Then, any element of the vector space can be represented as a linear combination of the basis vectors. I use square brackets to identify elements of the vector space. The coefficients of the basis vectors are called tristimulus values. A color space is associated with a specific viewer. The tristimulus values provide coordinates for elements of the vector space with respect to this basis. A standard observer has been adopted by the CIE to represent a typical human viewer with normal color vision. The set of physically realizable colors is a subset of the color vector space. It has the form of a cone, as illustrated in this figure. The usual display primaries are red, green, and blue. Any colors that are synthesized as a positive linear combination of these primaries lie in a cone with a triangular cross section. Color coordinates are used to identify specific colors within the color space. The basic representation is given by tristimulus values with respect to a given set of primaries. There are many different sets of primaries used in practice with different advantages. Each provides a different coordinate system. Changing the representation between different sets of primaries is a change of basis operation from linear algebra. This is presented in detail in the chapter along with various sets of primaries. The linear coordinates given by tristimulus values have the disadvantage of being highly perceptually non-uniform. Euclidean distance in the color space is not a good measure of perceptual color difference. The chapter presents a number of approximately perceptually uniform color coordinate systems, such as CIE-LAB. We often see in the literature different color coordinate systems referred to as different color spaces, such as RGB space, XYZ space, LAB space. However, I reserve the term color space for the set of colors associated with a specific viewer or device. Chapter 8 colors the processing of color signals, specifically signals and systems theory for signals with range in the color vector space. The main topics are linear shift invariant systems and frequency domain analysis and sampling theory. Color signals are often sampled with different sampling structure for different coordinates, such as in color filter arrays in digital cameras and mosaic displays. These are covered in the chapter. Color system signal has range in the color vector space and a signal domain of 2 or 3 dimensions. With a given set of primaries, the color image is represented by 3 component images. That is, 3 scalar images. A general linear shift invariant system for color images is formed of 9 scalar systems, since all 3 input components can contribute to the formation of each of the 3 output components. Most presentations of color image processing assume that each component image is processed separately, which is a significant restriction. Frequency response and Fourier analysis for systems operating on color signals are presented in the chapter. And a significant unique topic that is addressed in this book is that different components are often sampled on different sampling structures. As an example, this figure shows a portion of the color filter array sampling of the motorcycle's image with the Bayer color filter array. We see that red, green, and blue components are sampled on disjoint sampling structures. Analysis of this situation is a novel aspect of the book. The chapter also presents the topic of display mosaics, where again, different components are sampled on different sampling structures. Chapter 9 provides basic introduction to random field models. The main emphasis is to introduce wide-sense stationary random field models, which can be very helpful in designing basic image processing algorithms. One notable feature is the presentation of vector value random fields, particularly as applies to color images. The chapter presents methods to estimate spectral densities. These are later used in image processing examples. Chapter 9 concentrates on wide-sense stationary random field models. These are essentially shift-invariant models. A wide-sense stationary random field can be characterized by its autocorrelation function, which depends only on vector difference between 2 points in the domain. In this equation, it does not depend on the position W. An equivalent and in some ways more useful characterization is the power density spectrum, which is given by the multidimensional Fourier transform of the autocorrelation function. Later chapters give a few examples of the use of power density spectrum to guide filter design. Chapter also introduces the spectral density matrix for vector-valued random fields, specifically for application to color signals. Chapter concludes by demonstrating the effect of sampling and linear shift invariant filtering on a wide-sense stationary random field. It also presents some basic methods for estimating the spectral density or spectral density matrix. As an example, we applied the spectral density estimation method to this halftone image of the author from 1963. This plot shows the power density spectrum estimate of the halftone image. The plot clearly shows the location in the frequency domain of the spectral replicas introduced by the halftone process. This can be used to guide a filter design process as shown in the next chapter. Chapter 10 presents some elements of multidimensional filter design. The chapter focuses on finite impulse response, or FIR filters, since linear phase response is usually very important in image processing. Various filter design methodologies are presented. The chapter begins with an analysis of commonly used filter types, namely moving average and Gaussian filters, and studies their frequency response. I next discuss how low-pass filters can be converted into bandpass and bandstop filters by modulation of the impulse response. Two particular design methods are presented to approximate a desired frequency response. First is the window method, where the infinite impulse response of the ideal filter is limited to a finite support using a window function. Next, an optimization method is described that minimizes the average peak power of the error between the actual and the ideal frequency responses over the unit cell of the reciprocal lattice. Quality constraints on both the frequency response and the impulse response can be imposed. The filter design methods described in the chapter were implemented in MATLAB, and the software used is provided on the book's website. This figure shows an example of a low-pass filter designed with the least peak optimization method described in the chapter. The ideal response here has diamond-shaped passband and stopband edges. These figures show the spectral density of the halftone image shown previously before and after filtering with a multi-stop filter designed using the methods of the chapter. You can see how the spectral repeats have been eliminated. This image, this figure shows on the left the original halftone image I showed before, and then on the right it shows it filtered with the multi-stop band filter that was shown on the previous slide. So we see how the halftone pattern has been removed by this filtering operation. Chapter 11 is entitled Changing the Sampling Structure of an Image, but in fact it applies to any multidimensional signal defined on a lattice. The problem addressed in this chapter is to convert a signal defined on one lattice to be sampled on a different lattice. This is accomplished by a multidimensional system where the input and output signal spaces are different, associated with different lattices. The process may either increase the sampling density or decrease the sampling density. When decreasing the sampling density, we must be careful to control aliasing. The general approach described in the chapter involves linear upsampling and downsampling operations. Specifically, the conversion is done by upsampling to a common superlattice and then downsampling to the output lattice. The overall system is linear, but not shift invariant. In fact, it is periodically shift variant. Filter design methodologies using the methods of Chapter 10 are presented. This figure shows the general scenario addressed in this chapter. The input signal is defined on lattice lambda 1, shown here with the bullet symbol. The desired output signal is defined on lattice lambda 2, shown here with the square symbol. We notice that neither lattice is a sublattice of the other. The approach is then to upsample to the input signal to the least common superlattice, which is shown to be the lattice lambda 1 plus lambda 2, indicated here with the dot symbol, and then downsample this to the output lattice lambda 2. The overall structure is shown in this figure. The signal is upsampled to lambda 1 plus lambda 2 by inserting zeros at the points of lambda 1 plus lambda 2 that are not in lambda 1. The LSI filter H serves both as an interpolator to fill in the zeros and an anti-aliasing filter if the overall sampling density is decreased. The output of the filter is downsampled to lambda 2 by simply discarding the samples that are not on lambda 2. In practice, this should be implemented using a polyphase structure. This is mentioned in the book but not developed. An addendum to the chapter will be published on the book website describing the polyphase methodology in detail. Chapter 12 presents a novel contribution on symmetry invariant signals and systems. This extends the notion of shift invariance to other symmetries such as rotations and reflections. The figure on this slide shows a sinusoid with 8-fold symmetry. It is an eigenfunction for a certain category of symmetry invariant systems. This signal is invariant under rotations by multiples of 90 degrees and by reflections about the axes shown here in blue and red. The chapter considers first the case of aperiodic signals and then considers periodic signals. The case of periodic signals leads to an extension of the multidimensional discrete Fourier transform to more general lattices. A symmetry is a transformation that leaves some entity or object unchanged. For example, a rotation by 90 degrees of a square leaves it unchanged. Similarly, a shift of a lattice by any element of the lattice results in exactly the same set of points. Other possible symmetries of a lattice include rotations and reflections, depending on the lattice. This chapter extends the notion of shift invariant systems to more general symmetry invariant systems for different categories of lattices. Finding the eigenfunctions and eigenvalues of these types of systems leads to a general class of Fourier type transform, which includes the ubiquitous discrete cosine transform as an example. This chapter makes extensive use of the concept of symmetry group of a lattice. I make a lot of use of group theory from the field of abstract algebra and summarize a few basic ideas in Appendix B. Symmetry groups of lattices have been studied for a long time and are widely used in fields such as crystallography. There are different classes of lattices that exhibit more or less symmetry. The following slide shows different categories of two-dimensional lattices based on how much symmetry they have. The slide shows a classification of two-dimensional lattices based on their symmetry, where the amount of symmetry increases as we go down in the slide. Any lattice is of the parallelogram class. This has the identity and the inversion about the origin as symmetries. The regular hexagon lattice at the bottom has the most symmetry, with a symmetry group of order 12, 6 rotations, and by multiples of 60 degrees, and 6 reflections about various axes. In this chapter, I developed symmetry invariant systems, first for aperiodic discrete domain signal spaces, and then for periodic discrete domain signal spaces. For aperiodic signal spaces, the symmetries just have to leave the sampling lattice unchanged. For periodic signal spaces, related symmetries must also leave the periodicity lattice unchanged. These conditions are developed in the chapter. As in the case of shift invariant systems, we're interested in the eigenfunctions and of symmetry invariant systems in order to perform Fourier type analysis. These eigenfunctions are obtained by applying the symmetries of the symmetry group to complex exponentials and adding, as shown as this typical equation. Then, any element of the signal space can be expanded in terms of these eigenfunctions using a generalized version of Fourier analysis. The details are developed in the chapter. We can create a symmetric periodic signal by taking a block or portion of an image, applying symmetries, and then extending periodically. This figure illustrates portions of the motorcycle images seen before, to which we apply symmetries and then extend periodically. The four cases shows are no symmetry, inversion or twofold symmetry, quadrantal or fourfold symmetry, and eightfold symmetry. The important point to note is that the first two cases have sharp discontinuities, while the latter two do not. This makes these latter two much more amenable to image compression operations. The last section of the chapter shows how this idea can be applied to block-based image representation, similar to the DCT approach widely used in image and video compression standards. To conclude, I would like to summarize the main points I've made in this presentation. The book presents the main elements of multidimensional signal processing, with image and video processing as the main examples. A common framework and exposition method is used for the four categories of signal spaces, namely continuous domain and discrete domain signal spaces, both aperiodic and periodic. Lattices are used to specify both sampling structures and signal periodicities. This is used from the very beginning and is not presented as a specialized extension. I particularly favor basis-independent representations that do not change as we change the basis for the lattices. I also avoid normalized representations for signals in Fourier transforms that lose the geometric structure of these domains. I present the vector space approach for a representation of color and use this as the basis for the theory of color image processing. Conclude the book with several special topics, namely random fields, filter design, sampling structure conversion, and symmetry invariant signal processing. The final chapter presents all the needed development of lattice theory in one self-contained exposition. There's a companion website at the URL shown here. This website is in ongoing development and contains a number of useful resources for users of the book. These include MATLAB routines to reproduce the figures and results in the book, organized by chapter, plus utilities and data. MATLAB routines for spectral estimation and filter design are also included in the utilities section. There is a solutions manual with all my solutions for the problems included in the book. As errata sheet, and of course I welcome all contributions to this errata sheet, and other materials such as the large table of Fourier transform properties and this presentation, and other material is currently under development. Thank you, and please enjoy this photo showing a great deal of symmetry which is taken from the Alhambra.